Hi everyone. Today I'm going to talk about Merkle tree. So first I will quickly go through the traditional Merkle trees, and then I will introduce generalized Merkle tree in Plonky tree and also the MMCS in Plonky tree. So let's begin. Merkle tree is a data structure used to verify the integrity of data. You can prove a number is in the tree, and it allows for efficient and secure verification of data integrity. Why we use Merkle tree, lots of use cases, especially in crypto world. If you are new to Merkle tree, this example may help you. Imagine you have four data. You have four numbers, A, B, C, and D. So you will construct a Merkle tree like this. Hash 0, hash 1 root. So firstly, we build a Merkle tree by compute the hash of A and B and hash of C and D, and we get hash 0 and hash 1, and then we hash them together to get to the root. So the second operation is you can prove B is in the tree. So you just compute the Merkle proof A and hash 1, and then you send the Merkle proof to me. I can verify the Merkle proof, ensuring B is in the tree. So I have A, B, hash 1 and root, so that I can verify B is indeed in the tree. This is an example code of Merkle tree. Build tree, get proof, verify proof. Same example as above. A, B, C, D, you prove B is in the tree, and then I can verify B is indeed in the tree, so that the proof is valid. Yeah, let's jump into the generalized Merkle tree. So why we need generalized Merkle tree? In the traditional Merkle trees, one node equals to one number or one data block, and all the data are homomorphic. They are of the same size and structure. But actually in zero knowledge proof, we have in stars, we have polynomials with different degrees. So if we use a traditional Merkle tree, for example, for 5 polynomials, we need to use 5 Merkle tree because they are of different degrees. We cannot combine them together. But with generalized Merkle tree, we can combine 5 polynomials with different degrees and commit them in the same Merkle tree. Let's use a concrete example. The first example is we have matrices with same dimensions. We have 4 matrices with the same dimension, 8 rows, 1 column. So each row here is each column here is a matrix. This is matrix 1, matrix 2, matrix 3, and matrix 4. And we combine them together, we get 8 rows and 4 columns. So, and the Merkle tree is here. The Merkle tree has 8 nodes, and each node will equals to the hash of the row. Yeah. in this way we compress 4 matrices into one Merkle tree. We compress 4 elements into one node. And the second example is how about matrices with different dimensions? So in this example, we also have 4 matrices. The 3 of them are with same row number. They all have 4 rows, like this, 4 types, 4 rows, 3 columns, 4 rows, 2 columns, 4 rows, 4 rows, 4 columns. And there's a smaller one which is 2 times 2. And in this way we construct a Merkle tree like this. In the lower level, in the lowest level nodes, which is the leaves, we construct L0 equals to all the elements from the first row, and L1 equals to all the elements in the second row. This is similar as the example above, where you compress all the elements from the same row into one node. And in upper layer, we include the smaller matrices here. We include it here like this. We, aside from hash 2 leaves, leaf 0 and leaf 1, we add in 0, which is in 0 is the row of the small matrix. And for here, the in 1 is the hash of the second row in the small matrices. And in that way, we successfully compress and commit 4 matrices with different dimensions into one Merkle tree. And this is very useful in practical, in Stark. So with the generalized Merkle tree, it is easier to transform it to MMCS, a mixed matrix commit scheme. And MMCS is a generalization of a vector commitment scheme, so that in Plonky-free, using MMCS, we can commit to matrices in different dimensions and then opening rows. So it is how it works. It just is almost the same as the generalized Merkle tree. And you just refer to the upper part. The last question is why MMCS? Recall that in stars, it requires to commit multiple polynomials with different degrees. Like the execution trace contains multiple columns, and this is a matrix. And the quotient composition polynomial, this is another vector. The polynomials in 5 folding ones, we have one polynomial. There are lots of polynomials in here. So if we don't use MMCS, we need to use 10s or 20s Merkle tree in order to commit all of this. But with MMCS, we can compress all of them together, even these polynomials, these matrices are in different degrees, are in different size. we can commit all of them in one tree, and this will save a lot. Yeah, that's it.